Tonight, we're going to answer a question that sounds simple but reaches all the way down to the strangest layer of reality we've ever found. Where does an electron get its energy? You've heard about electrons your whole life. They're in your atoms, in your wires, in every chemical bond holding your body together. They're the reason your phone screen lights up, the reason lightning strikes, the reason anything in the universe is solid at all. But here's what most people never stop to ask. An electron is always moving. It never slows down. It never drains like a battery. It never runs out. And no one ever charged it up. By the end of tonight, you're going to understand exactly where that energy comes from, why the electron can't stop even if it wanted to, and what that tells us about the nature of reality at its most fundamental level. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something you already know. A ball rolling across the floor eventually stops. Friction bleeds away its energy. The kinetic energy gets converted into heat, into tiny vibrations of the floor and the air, and the ball comes to rest. That's the world you live in. Energy flows from ordered motion into disordered heat. Things slow down. Systems run down. Everything eventually reaches equilibrium. This is so deeply embedded in your intuition that it feels like a universal law. And for most of the world you can see, it is. A car runs out of gas. A pendulum swings lower and lower. A cup of hot coffee cools toward room temperature. Every system you encounter in daily life bleeds energy. Something fuels it, or it stops. That's the baseline assumption your brain has built up over a lifetime of experience. But the world you can see is built out of something far stranger. Inside every atom in the floor, the ball is rolling across. Electrons are moving. They've been moving since those atoms formed, billions of years ago in the cores of stars long since gone. And they haven't slowed down, not a fraction, not even a little. The electron in a hydrogen atom today is moving with exactly as much energy as it had when that hydrogen atom first formed in the early universe, 13.8 billion years ago. That number should stop you cold, because it violates everything your intuition tells you about how energy works. If something is moving, something else had to set it moving. And if it keeps moving, something has to keep supplying the energy, doesn't it? The answer, it turns out, is no. And that no is the beginning of quantum mechanics. To understand the electron's energy, you first have to understand what an electron actually is. Not what your high school chemistry teacher drew on the board. Not a tiny planet orbiting a nucleus. Not a little sphere of negative charge tracing a circular path like some miniature satellite. That picture, as useful as it is for chemistry class, is wrong in almost every meaningful way. The real picture was worked out in the 1920s, mostly by people who were disturbed by what they were finding. Werner Heisenberg was 23 years old when he developed the first version of quantum mechanics in 1925. He did it while recovering from hay fever on the island of Helgoland, away from his distractions in Göttingen. He stayed up all night working through the mathematics, and by 3 a.m, he had something that seemed to work. He was shaken enough by what he'd found that he went for a walk on the rocks before sunrise. He later said he felt he was looking at the face of a deep, underlying truth in nature. Erwin Schrödinger came at the same problem from a different angle the following year. His wave equation describes the evolution of the quantum state over time. He found it while on a holiday in the Swiss Alps in late 1925 and early 1926. The story goes that he brought a girlfriend he hadn't introduced to his wife, and whoever she was, the holiday produced one of the most important equations in physics. Niels Bohr, who had given us an early model of the atom in 1913, spent years afterward arguing with Heisenberg and Schrödinger about what quantum mechanics actually meant. He never stopped being unsettled by it. He said that if you weren't shocked by quantum mechanics, you hadn't understood it. Paul Dirac, the British physicist who combined quantum mechanics with special relativity in 1928, was famously quiet and precise. He predicted the existence of antimatter before it was discovered, purely from the mathematics of his equation. Max Born gave us the interpretation that the square of the wave function is a probability. He said this, almost as an aside, in a paper in 1926, and it turned out to be the right interpretation. These were not people prone to exaggeration. These were careful, brilliant, mathematically rigorous scientists. And they were all shaken by what they found. What they found, working through the mathematics in those 2 or 3 crucial years, shattered the common sense of everyone involved. An electron is not a particle in the way you think of particles. It's not a tiny billiard ball sitting at a specific location. It's a quantum object, which means it exists in a superposition of states. It doesn't have a definite position until something measures it. It doesn't have a definite momentum until something measures that. Before measurement, it's smeared across space, described by a mathematical object called a wave function. The wave function is usually written as the Greek letter psi. It's a complex valued function of space and time. The square of its absolute value gives you the probability density of finding the electron at any given location if you decide to look. This is not a statement about ignorance. It's not that the electron is somewhere and you just don't know where. It's that the question of where the electron is doesn't have a definite answer until you ask it, until you perform a measurement that forces the wave function to give up a specific value. This is the part of quantum mechanics that made Einstein uncomfortable for his entire life. He spent years trying to find a way out, trying to show that quantum mechanics was incomplete, that there had to be hidden variables underneath, determining things in a classical way. He couldn't find one. Nobody has. The universe plays dice. The electron is one of the dice, and its energy is one of the things you get to roll for. Now here's where the energy question starts to get genuinely interesting. In classical physics, an electron orbiting a nucleus would behave like a satellite orbiting a planet. The electron would spiral inward as it lost energy to electromagnetic radiation. An accelerating charge radiates energy. That is a firm result of Maxwell's equations, the laws governing electricity and magnetism. James Clerk Maxwell wrote down these equations in the 1860s, synthesizing everything known at the time about electricity, magnetism, and light into 4 elegant equations. Those equations predicted that light was an electromagnetic wave. They turned out to be exactly right. They're still exactly right. And one thing those equations say clearly is that an accelerating charge radiates. An electron moving in a circular orbit is constantly accelerating, not because it's speeding up or slowing down, because its direction is always changing. Circular motion requires a centripetal acceleration pointing inward toward the center at all times. That's acceleration. And an accelerating charge radiates energy. The calculation is straightforward. An electron in a circular orbit around a proton would lose energy through radiation and spiral inward in about 10 to the power of negative 11 seconds. 1/100th of a billionth of a second. Every hydrogen atom should collapse almost before it forms. Every atom of every element should collapse in the same tiny fraction of a second. Matter, as we know it, should not exist. You should not exist. The fact that you're reading this, the fact that atoms are stable, the fact that matter holds together at all, is proof that classical physics breaks down completely at the atomic scale. Quantum mechanics is what takes over, and it changes everything about how we think about energy. In quantum mechanics, electrons don't orbit the nucleus in circular paths. They occupy what physicists call orbitals, not to be confused with orbits. An orbital is a region of space where the electron is most likely to be found. It's a probability cloud. It has a specific shape, a specific size, and crucially, a specific energy. The shapes of these orbitals are derived directly from the mathematics of the Schrödinger equation applied to the electromagnetic attraction between the electron and the nucleus. The simplest orbital, the one the electron occupies in its lowest energy state in hydrogen, is a perfect sphere. The electron has equal probability of being found in any direction from the nucleus. The most likely distance from the nucleus is about 53 picometers, 53 times 10 to the power of negative 12 meters, about 50 billionths of a millimeter. That's the Bohr radius, named after Niels Bohr, who estimated it in his early model. The next set of orbitals have different shapes. Some are spherical. Some are shaped like dumbbells, with two lobes pointing in opposite directions. Some are shaped like four-leaf clovers. These shapes are not arbitrary. They're solutions to a differential equation. They're the shapes that satisfy the quantum mechanical rules for a particle in the electromagnetic potential of the nucleus. And each shape, each orbital, comes with a specific, fixed energy. The key word is specific. The electron in a hydrogen atom doesn't get to have just any energy. It can only have certain allowed energies. These are called energy levels. The lowest possible energy level is called the ground state. The higher energy levels are called excited states. The electron is only allowed to exist at these discrete steps, not between them, never in between. This quantization of energy is one of the most fundamental results of quantum mechanics. It's the reason the field is called quantum mechanics in the first place. Quantum means discrete. The energy doesn't flow continuously, like water. It comes in specific, indivisible packets. The lowest energy level, the ground state of hydrogen, sits at negative 13.6 electron volts. An electron volt is a unit of energy. It's the amount of energy an electron gains when it accelerates through a potential difference of 1 volt. In more familiar units, 1 electron volt equals about 1.6 times 10 to the power of negative 19 joules. A tiny amount of energy by everyday standards. But at the atomic scale, it's exactly the right unit. The negative sign in negative 13.6 electron volts matters enormously. It means the electron is bound to the nucleus. You'd have to supply 13.6 electron volts of energy to rip that electron completely free. That's the ionization energy of hydrogen. The next allowed energy level sits at negative 3.4 electron volts. The one above that at negative 1.5 electron volts. Then negative 0.85 electron volts. Then negative 0.54 electron volts. These aren't arbitrary numbers, chosen for convenience. They come directly out of the mathematics when you solve the Schrödinger equation for the electromagnetic attraction between an electron and a proton. You solve the equation. The energy levels fall out. They've been confirmed by experiment to extraordinary precision. Every hydrogen atom in the universe has electrons sitting at exactly these levels. Not approximately, exactly. The universe does not waver on this point. A hydrogen atom on the far side of the Andromeda galaxy has the same energy levels as the hydrogen atom in the water molecule you just drank. Same levels, same energies, same quantum mechanics. The laws don't change with location. So, an electron in the ground state of hydrogen has 13.6 electron volts of energy, measured relative to a free electron at rest. But where did that energy come from? The honest answer begins with the electromagnetic force. An electron carries a negative electric charge. A proton carries a positive electric charge. Opposite charges attract. This is Coulomb's law, discovered by Charles Augustin de Coulomb in 1785, and it's one of the most precisely verified laws in nature. The force between two charges falls off as the square of the distance between them. Halve the distance and the force quadruples. Double the distance and the force drops to a quarter. This inverse square law is fundamental. When you bring an electron close to a proton, the electromagnetic attraction pulls them together. As the electron falls toward the proton, it gains kinetic energy, exactly the way a ball gains speed as it falls toward Earth under gravity. That kinetic energy has to come from somewhere. It comes from the potential energy stored in the electric field between the two charges. When two opposite charges are separated, there is potential energy in the electric field between them. That energy is stored in the field itself. When they come closer together, that potential energy converts to kinetic energy. This is exactly analogous to gravitational potential energy. A rock at the top of a cliff has more gravitational potential energy than a rock at the bottom. Roll it off, and the potential energy converts to kinetic energy. The rock gains speed as it falls. Bring the electron close to the proton, and the electrostatic potential energy converts to kinetic energy. The electron gains speed as it falls inward. So, at the simplest level, the electron's energy in an atom comes from the electromagnetic interaction between the electron and the nucleus. It's the energy released when opposite charges come together. This is a satisfying answer as far as it goes, but it immediately raises another question. If the electron is falling toward the proton, gaining kinetic energy, why doesn't it fall all the way in? Why does it stop at a specific distance? Why doesn't it crash into the nucleus? Here is where quantum mechanics does something genuinely remarkable. In classical physics, the electron would spiral inward, radiating energy, and collapse into the nucleus in a tiny fraction of a second. Quantum mechanics prevents this with something called the Heisenberg uncertainty principle. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that you cannot simultaneously know the exact position and the exact momentum of a particle. The more precisely you know where something is, the less precisely you can know how fast it's moving and in what direction, and vice versa. This is not a statement about the limits of your measuring instruments. It's not that the tools are too clumsy or the sensors too imprecise. You can't make more precise instruments and get around it. It's built into the fabric of reality itself. Position and momentum are fundamentally complementary. Pinning down one makes the other blur. The mathematical statement is that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4 pi. Planck's constant is about 6.6 times 10 to the power of negative 34 joule-seconds. An almost incomprehensibly small number, but not zero. And that's the crucial point. Not zero. Now, think about what happens as an electron approaches a nucleus. If the electron got very close to the nucleus, you'd know its position very precisely. It would be squeezed into a tiny region of space. But the uncertainty principle says that if its position is very precisely known, its momentum must be very uncertain. Highly uncertain momentum means the electron could be moving in any direction with any speed across a huge range. A large spread of possible momenta means a large average kinetic energy. The more tightly you try to confine the electron, the more violently it must be moving on average. This is not a metaphor. The electron genuinely has an enormous range of possible momenta when confined to a tiny space, and that translates directly into enormous average kinetic energy. Physicists call this the zero-point energy. It's the minimum energy the electron must have simply because it's confined to a finite region. It exists even at absolute zero temperature, even when there's no thermal energy whatsoever. It's intrinsic to confinement itself. So, here's the balance that stabilizes the atom. The electromagnetic attraction between the electron and the proton pulls the electron inward, lowering the potential energy as they get closer. But the uncertainty principle pushes back. The more tightly you confine the electron, the more kinetic energy it must have. These two effects compete. The ground state of the hydrogen atom is the point where these two competing effects reach a balance. The point where the total energy, kinetic plus potential, is at its minimum. Pull the electron inward from there, and the kinetic energy goes up faster than the potential energy comes down. The electron springs back outward. Push the electron outward from there, and the potential energy goes up because you're moving the opposite charges apart. The electron falls back in. The ground state is a balance point, a quantum mechanical equilibrium enforced not by some external containment, but by the laws of physics themselves. The electron can't fall lower because falling lower would increase the total energy. That's the ground state, the floor of the possible. This is not because of some special property of electrons alone. It's because of the uncertainty principle. Because confining any quantum object to a small region of space necessarily gives it kinetic energy. The ground state of hydrogen is the configuration where the total energy is minimized. That minimum exists because of quantum mechanics. And that's why matter is stable. That's why you don't dissolve. At a certain level, that's the answer. The electron's energy in its ground state comes from the interplay between electrostatic attraction and the quantum mechanical cost of confinement. Without quantum mechanics, no atom would hold together. Without quantum mechanics, there would be no chemistry, no molecules, no stars, no planets, and no one to ask these questions. But let's go deeper, because the question of where the energy comes from has another layer. When an atom forms, energy is released. If you combine a proton and an electron to make a hydrogen atom, the system releases 13.6 electron volts of energy. That energy goes somewhere. Usually, it gets carried away by a photon. A photon is a quantum of the electromagnetic field. It's a packet of light. And this is where the story of electron energy connects to something even more fundamental. When that photon is absorbed by an electron, the electron jumps to a higher energy level. When the electron drops back down, it emits a photon. The photon carries away the energy difference between the two levels. This exchange is incredibly precise. A hydrogen electron dropping from the second energy level to the first emits a photon with a wavelength of exactly 121.6 nanometers. This is in the ultraviolet part of the spectrum, just beyond what human eyes can see. Every hydrogen atom in the universe that undergoes this particular transition emits that exact wavelength. Not approximately. Exactly. The photon carries a specific energy equal to the difference between the two levels. That energy equals Planck's constant multiplied by the frequency of the light. This is the equation Max Planck wrote down in 1900 to explain the spectrum of black-body radiation, and it changed physics forever. Energy equals Planck's constant times frequency. It means energy comes in packets tied to the frequency of the associated light. Low-frequency light carries low-energy packets. High-frequency light carries high-energy packets. Radio waves carry the least energetic photons. Infrared carries slightly more. Visible light carries photons with energies between about 1.8 and 3.1 electron volts. Ultraviolet carries more. X-rays carry more still. Gamma rays carry the most energy per photon of any electromagnetic radiation. This is why gamma rays are so damaging to biological tissue. Each photon packs enough energy to break chemical bonds, strip electrons from atoms, and disrupt DNA. The electron is constantly participating in this dance. In atoms, in molecules, in materials, electrons are absorbing and emitting photons, jumping between energy levels, exchanging energy with the electromagnetic field. The electron's energy is never really its own. It's in constant dialogue with the field, and the field is everywhere. Let's look at what actually happens when light interacts with matter. Take a hydrogen atom sitting in space. A photon comes along. If the photon carries exactly the right energy to kick the electron from one allowed level to another, the atom absorbs it. The electron jumps up. If the photon carries more or less than the exact right amount, the atom ignores it entirely. The electron doesn't budge. Why would an atom be so picky? Because the energy levels are discrete. There's nowhere for the electron to go unless the photon carries exactly the energy corresponding to the gap between levels. It's like a staircase. You can stand on the first step. You can stand on the second step. You cannot stand between the steps. You can jump from the first to the second if someone gives you exactly enough energy to make that jump. Too little, and you don't make it. Too much, and there's nowhere to put the excess. The atom either absorbs the whole photon at the exact right energy, or it doesn't absorb it at all. This explains one of the most powerful tools in all of astronomy: spectroscopy. When you shine white light through a gas of hydrogen atoms, the hydrogen absorbs photons at specific wavelengths corresponding to the allowed transitions between energy levels. Pass that light through a prism after it exits the gas, and you see the full rainbow of the spectrum, but with dark lines at specific wavelengths. The dark lines are where the hydrogen absorbed the light. These absorption lines form a fingerprint, unique to hydrogen. No other element in the universe has the same set of lines, because no other element has the same energy levels. The energy levels depend on the number of protons in the nucleus and the quantum mechanical solutions to the electron's wave function in that electromagnetic field. Every element has a unique spectral fingerprint, and that fingerprint is visible in light from anywhere in the universe. Astronomers can look at the spectrum of a star 12 billion light-years away, identify the pattern of absorption lines, and determine exactly which elements are in that star's atmosphere. The temperature of the star, because hotter temperatures excite higher energy levels, producing different line patterns. Whether the star is moving toward us or away from us, because motion Doppler shifts the frequencies of the lines, moving them toward blue or toward red. Whether the star has a strong magnetic field, because magnetic fields split some spectral lines through a process called the Zeeman effect. Whether the star has a companion, because a companion star causes the primary star to wobble, producing periodic Doppler shifts. All of this information, encoded in the electron's energy levels, readable from light that has traveled for billions of years across the universe. The electron's quantum energy structure is a cosmic identification system, readable from anywhere in the observable universe. Joseph Fraunhofer first noticed the dark lines in the solar spectrum in 1814. He mapped over 500 of them without understanding what caused them. About 45 years later, Gustav Kirchhoff and Robert Bunsen figured out that each element produces its own characteristic set of lines. The dark lines in sunlight are the fingerprints of atoms absorbing specific frequencies in the sun's atmosphere. From that observation, we learned the composition of the sun without ever visiting it. We learned that the sun contains hydrogen, helium, oxygen, calcium, iron, magnesium, sodium, and dozens of other elements, all from the quantum energy levels of electrons, all from the discrete, specific steps on the staircase. The electron in the second energy level of hydrogen won't stay there long. It's in an excited state. It can drop back down. And when it does, it emits a photon with exactly the right energy to account for the difference between levels. The average time for a hydrogen electron in the second energy level to drop back to the ground state is about a nanosecond, a billionth of a second. But it's not zero. During that nanosecond, the electron is genuinely in the higher energy state. It absorbed energy from a photon. The photon's energy came from whatever emitted the photon in the first place. Maybe a hotter atom nearby. Maybe a collision between atoms. Maybe ultraviolet light from a hot star. The energy traces back through a chain of events. But the electron's energy is always discrete, always quantized, and always governed by the specific energy levels allowed by the quantum mechanics of that particular atom. The electron doesn't get to choose its energy level. The laws of physics choose for it. And those laws apply identically everywhere in the universe. The hydrogen atom, in a nebula 3 billion light-years away, obeys exactly the same quantum mechanical rules as the hydrogen atom in a water molecule in your body. The same energy levels, the same transitions, the same photon wavelengths. The universe is consistent in this way. The laws of physics are the same everywhere we've looked. And nowhere is that more visibly confirmed than in the universal consistency of atomic spectral lines. Now let's go somewhere more complex. Real atoms are not just hydrogen. Hydrogen has 1 proton and 1 electron. But helium has 2 protons and 2 electrons. Carbon has 6 protons and 6 electrons. Oxygen has 8 of each. Iron has 26. Gold has 79. Uranium has 92. With multiple electrons, the story gets richer and more subtle, because electrons are fermions. In quantum mechanics, all particles fall into one of two fundamental categories: bosons and fermions. Bosons are particles with integer spin, 0, 1, 2. Photons are bosons with a spin of 1. The Higgs boson, whose existence was confirmed by experiments at the Large Hadron Collider at CERN in 2012, is a boson with a spin of 0. Bosons have a remarkable property. They don't mind sharing. You can pile as many bosons as you like into the same quantum state. This is why lasers work. A laser produces an enormous number of photons, all in the same quantum state, all with the same frequency, all moving in the same direction, all with the same phase. The photons march together in perfect lockstep because they're bosons, and bosons love company. Fermions are different. Fermions are particles with half-integer spin, 1/2, 3/2. Electrons have a spin of 1/2. Quarks have a spin of 1/2. Protons and neutrons, which are made of quarks, also behave as spin 1/2 particles in most situations. And fermions are fundamentally antisocial. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, states that no two identical fermions can occupy the same quantum state simultaneously. This is one of the most important statements in all of physics. It's not an empirical rule discovered by looking at atoms and noticing a pattern. It's derived from the deep mathematics of quantum field theory. It follows from the requirement that the wave function describing multiple identical fermions must be antisymmetric under the exchange of any two particles. If you mathematically swap two identical fermions in the wave function must pick up a minus sign. And if the two fermions were in the same quantum state, swapping them would give you the same state with a minus sign. The only number that equals its own negative is 0. So the wave function for two identical fermions in the same quantum state is identically 0. The probability is 0, not small. 0, not sometimes 0. Always 0. It never happens. In any atom with more than one electron, the electrons have to stack up in the energy levels. 2 electrons, and only 2, can sit in the lowest energy level, one with spin pointing up, one with spin pointing down. Those are the only 2 available quantum states in the ground level. Both slots are filled. The next electrons have to go into the second energy level. This level has more allowed quantum states, but still a finite number. 8 electrons can fit before all the states are occupied. Then, the third level, with room for 18. The fourth, for 32. This filling up process is why the periodic table looks the way it does. Elements in the same column of the periodic table have the same number of electrons in their outermost shell. They behave chemically in similar ways because the outermost electrons are the ones that interact with other atoms. Lithium, sodium, potassium, rubidium, cesium, and francium, all in the first column, all with 1 electron in their outer shell, all highly reactive, all prone to losing that outer electron easily. Fluorine, chlorine, bromine, iodine, astatine, all in the second to last column, all with 7 electrons in their outer shell, wanting 1 more to complete it. All highly reactive, all prone to grabbing electrons from other atoms: helium, neon, argon, krypton, xenon, radon, all in the last column, all with completely full outer shells. all chemically inert, all reluctant to interact with anything. Argon fills a room and does nothing. It doesn't corrode. It doesn't react. It doesn't combine with other atoms, because its outer shell is full. The electrons have nowhere to go, no empty states to jump into, no room at the inn. The Pauli exclusion principle locks them in place. The Pauli exclusion principle creates the structure of the periodic table. The periodic table creates chemistry. Chemistry creates molecules. Molecules create biology. The electron's quantum nature, the fact that it's a fermion subject to this rule, is the reason any of this complexity exists at all. Let's make this concrete with carbon. Carbon has 6 protons in its nucleus and 6 electrons. 2 electrons fill the first shell completely. The remaining 4 electrons go into the second shell, which has room for 8. Those 4 outer electrons are the valence electrons. Carbon's 4 valence electrons sit in the second shell, a half-filled shell. That makes carbon something special. It can form 4 bonds, tetrahedral bonds. 4 bonds pointing outward toward the 4 corners of a regular tetrahedron, the most symmetric 3-dimensional arrangement possible. This ability to form 4 bonds in 3-dimensional space makes carbon the most versatile chemical building material in the universe. Carbon can link to other carbon atoms in chains. Carbon chains with hydrogen atoms attached form the simplest organic molecules: methane, ethane, propane. The fuels in your gas stove. Carbon, arranged in hexagonal rings, forms benzene. Carbon rings linked together form polycyclic hydrocarbons. Carbon atoms bonded to 4 other carbons, each bonded to 4 more carbons, extending outward in 3 dimensions in a tetrahedral lattice, creates a crystal of diamond, the hardest natural material on Earth. The most transparent material at room temperature to a wide range of wavelengths. The material with the highest thermal conductivity of any known substance. The same carbon atoms arranged in flat sheets, with each carbon bonded to 3 others in a hexagonal pattern, creates graphite, the soft black material in pencil leads. One arrangement of carbon atoms gives you diamond. Another gives you graphite. Same element. Same 6 electron per atom. The difference is only in which orbitals those outer electrons occupy and how they bond. Graphite conducts electricity because 1 electron per carbon atom is free to move between layers. Diamond doesn't conduct electricity at all. One arrangement of identical atoms. 2 completely different behaviors. All from the quantum mechanics of the electron's energy levels and orbitals. And this versatility is what makes life possible. The proteins in your muscles. The fats in your cell membranes. The sugars your cells burn for energy. The nucleotides in your DNA. All built from carbon chains and rings. All built from the tetrahedral bonding geometry of carbon's 4 valence electrons. All possible because of the Pauli exclusion principle, stacking electrons in shells and making carbon the element it is. The energy of every electron in every atom in your body is what it is because of quantum mechanics. And the fact that you have a body at all is for exactly the same reason. Let's look at electrons in a metal. Take a piece of copper wire. In a metal like copper, the outermost electrons from each copper atom are not bound to individual atoms. They're free to drift through the entire piece of metal. This is sometimes called the electron sea. Billions and billions of electrons moving through the copper, not tied to any particular atom. And these free electrons are still fermions. The Pauli exclusion principle still applies. They can't all pile into the same quantum state. So they have to spread out across a vast range of energy states. The lowest energy states fill up first, then higher ones, then higher ones. Still, in a piece of copper, at absolute zero temperature, the electrons fill up all available states up to a certain maximum energy. That maximum energy is called the Fermi energy, named after Enrico Fermi, who developed the statistical description of fermions in the late 1920s. For copper, the Fermi energy is about 7 electron volts at absolute zero temperature. No thermal energy at all. And yet the electrons have 7 electron volts of energy. Not because anything heated them, not because any external source supplied energy to them, just because they're fermions. Just because they can't all be in the same state. Just because the Pauli exclusion principle forces them to occupy states all the way up the energy scale, until all the electrons have found a home. This is a purely quantum mechanical effect. It has no classical equivalent, and the practical consequences are enormous. The electrical conductivity of metals depends on how easily electrons near the Fermi energy can be excited into slightly higher states where they can carry current in response to an electric field. The thermal conductivity of metals, which is why metal feels cold to the touch even at room temperature, is dominated by these same free electrons, carrying thermal energy through the material faster than atomic vibrations alone could carry it. The color of metals depends on how photons interact with electrons near the Fermi energy. Gold absorbs photons in the blue and violet part of the spectrum because the Fermi energy of gold's electrons is such that those photons can excite electronic transitions. The red and yellow photons pass through without being absorbed or are reflected. That's why gold looks gold. Silver's Fermi energy is different. It reflects across the whole visible spectrum more uniformly. That's why silver looks silver. Copper absorbs blue and reflects red and orange. The color you see when you look at a metal is the story of what's happening with the electron energies inside it. The visible world is a record of quantum mechanics playing out in every material. Semiconductors are even more dramatic. Silicon, germanium, gallium, arsenide, silicon carbide. These materials have a gap in their allowed energy levels, a forbidden zone. The valence band, the range of energies where electrons normally sit, is separated from the conduction band, where electrons can move freely and carry current, by this energy gap. In silicon, that gap is about 1.1 electron volts. At room temperature, the thermal energy available to electrons is about 1/40th of an electron volt. Almost none of the electrons have enough thermal energy to jump across the 1.1 electron volt gap. So pure silicon at room temperature conducts almost no electricity, but add a tiny amount of an impurity. Substitute a handful of phosphorus atoms among billions of silicon atoms. Phosphorus has 5 electrons in its outer shell. Silicon has 4. One of phosphorus's outer electrons doesn't fit neatly into the silicon crystal's valence band. It sits in an energy state just below the conduction band, just a fraction of an electron volt below the gap. At room temperature, thermal energy is enough to kick it across that tiny remaining gap. Suddenly, that electron is in the conduction band. Suddenly, it can move and carry current. A silicon crystal doped with phosphorus conducts electricity much more readily than pure silicon. You've made an N-type semiconductor. Extra electrons available to conduct. Dope silicon with boron instead. Boron has only 3 outer electrons. 3 bonds instead of 4. This creates a missing bond, a hole in the electron structure where an electron could sit but doesn't. Other electrons can hop into that hole, and as they do, the hole moves in the opposite direction. It behaves like a positive charge moving through the material. A p-type semiconductor. Put an n-type and a p-type region in contact, and you've made a diode. The junction between them creates an energy barrier. Current can flow easily in one direction, but not the other. This is the fundamental principle of rectification. The diode turns alternating current into direct current. It's in every power adapter you've ever owned. Put 3 layers together in the right configuration with a thin p-type layer between 2 n-type regions, and you've made a transistor. A device where a small signal applied to the middle layer controls a much larger current flowing through the outer layers. A switch. An amplifier. The transistor was first demonstrated at Bell Laboratories in December 1947 by John Bardeen, Walter Brattain, and William Shockley. Bardeen, Brattain, and Shockley shared the Nobel Prize in Physics in 1956. The first transistor was physically large. Today, the most advanced semiconductor chips contain transistors with features smaller than 10 nanometers. About 40 silicon atoms across. Over 100 billion transistors on a chip smaller than a postage stamp. Every one of those transistors works by manipulating the energy levels of electrons in semiconductors, by exploiting the energy gap between the valence band and the conduction band, by using impurities to place electron energy states exactly where you need them, by the deliberate, precise engineering of the quantum mechanical energy structure of electrons in materials. The entire digital world, every phone, every computer, every server, every satellite, every piece of modern infrastructure runs on the quantum mechanics of the electron and its discrete energy levels. The most advanced technology humanity has ever built is built on the strangeness of quantum mechanics, on the weirdness of the electron's energy, on the Pauli exclusion principle forcing electrons to stack up in materials in ways that create usable gaps and bands. We're living inside a technology that runs on the rules of the quantum world, and most people never think about it. Now let's go back to the question one more time with a sharper lens, because there's a deeper answer still waiting. In quantum field theory, the framework that unified quantum mechanics with special relativity and gave us the most precise physical theory in science, particles are not fundamental. Fields are fundamental. This is a shift so profound, it deserves a real pause. For centuries, physics was about particles. Billiard balls hitting each other. Planets pulling on each other through gravitational forces. Atoms exerting forces on atoms. Objects moving through space under the influence of forces. Quantum field theory says something more radical. The fundamental things are fields, not particles embedded in fields, not particles interacting through fields. Fields themselves, all the way down. The electromagnetic field fills all of space. It has done since shortly after the Big Bang. There is no region of the universe without an electromagnetic field. No corner, no gap, no empty region. The field is everywhere. The electron field fills all of space, everywhere, always. What we call an electron is a localized excitation of that field, a ripple, a disturbance, a quantized vibration. When an electron is created in a particle accelerator, the electron field is excited in a specific region. Energy goes in, an excitation appears. When an electron and its antimatter partner, the positron, meet and annihilate, the electron field returns toward its ground state in that region. And the energy is released as excitations of the electromagnetic field. Photons. The electron and the positron are like two excitations of the same underlying field. Create a pair, and you've created two excitations. Let them meet, and both excitations collapse, releasing energy as photons. Excitations of the electromagnetic field. Energy flowing from one set of field ripples to another. The total energy is conserved throughout. This is quantum electrodynamics. QED. The quantum field theory of electrons and photons and their interactions. Built by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s. All three independently developed the framework. All three shared the Nobel Prize in Physics in 1965. Feynman described QED as the jewel of physics. His way of approaching it, using diagrams to represent the different contributions to a calculation, became one of the most powerful tools in theoretical physics. Feynman diagrams are still used today in calculations across particle physics, condensed matter physics, and quantum gravity. QED makes predictions that have been confirmed to better than 1 part in 10 billion. The most precisely tested theory in the history of science. And what does QED say about the electron's energy? It says the electron's energy is the energy of a field excitation. The electron field has a ground state. In that ground state, with no excitations present, the field is not perfectly zero. Because the uncertainty principle applies to fields just as it applies to particles. You cannot have a field that is simultaneously perfectly zero in value and perfectly zero in rate of change. That would mean you know both the field's value and its rate of change exactly. The uncertainty principle forbids it. So even in the lowest energy state of the electron field, there are quantum fluctuations, restless vibrations, an irreducible background of activity that cannot be eliminated no matter how low the energy goes. This is the vacuum energy of the field, and the electron, as an excitation of that field, sits on top of that vacuum energy. Its energy is the energy of the excitation above the vacuum floor. The electromagnetic field has its own vacuum energy. The electron field has its own vacuum energy. Every quantum field in nature has a non-zero vacuum energy. When you add up all these contributions, you get the vacuum energy of the universe, the energy density of what we call empty space. This quantity has been calculated in quantum field theory, and the result is one of the most uncomfortable predictions in the history of physics. The naive calculation gives a vacuum energy density somewhere between 10 to the 60 and 10 to the 120 times larger than what we actually observe. This discrepancy is called the cosmological constant problem. It's widely considered the worst theoretical prediction in physics. Not wrong by 10%. Not wrong by a factor of 2. Wrong by at least 60 orders of magnitude. 60 powers of 10. Possibly 120 powers of 10. The calculation and the measurement disagree by a factor larger than the total number of atoms in the observable universe. And it's directly related to the question of where the electron gets its energy. Because the electron is embedded in these quantum fields. Its energy is tied up in the same vacuum fluctuations that contribute to the cosmological constant. The question of where the electron gets its energy is, at the deepest level, connected to the question of why the universe doesn't weigh catastrophically more than it does. Nobody has resolved this. Not yet. It remains one of the deepest open problems in all of theoretical physics. And it points to something we don't yet understand about the relationship between quantum mechanics and gravity. One of the most striking experimental confirmations of vacuum energy was predicted in 1948 by the Dutch physicist Hendrik Casimir. He calculated that if you take two uncharged, perfectly conducting metal plates and place them very close together in a vacuum, they should feel a tiny attractive force. Not because of any electric charge, not because of any conventional magnetic attraction, but because the vacuum energy between the plates is slightly lower than the vacuum energy outside the plates. Here's why. The region between the plates is constrained. The metal plates are conductors. The electromagnetic field has to satisfy specific boundary conditions at a conductor. The electric field parallel to the surface has to be zero at the surface. This means only electromagnetic field modes that fit exactly between the plates, with the right relationship between their wavelengths and the gap, are allowed inside. Outside the plates, all wavelengths are possible. All modes of the electromagnetic field can exist. So there are more field modes, more vacuum fluctuations, outside than inside. The vacuum energy between the plates is slightly lower. This difference in energy creates a pressure. The plates are pushed toward each other. The Casimir effect. It was first measured experimentally in 1958 by Marcus Sparnay. His measurement was rough, with large uncertainties. Subsequent, more precise measurements confirmed it beautifully. In 1997, Steve Lamoureux at the University of Washington measured it with an accuracy of 5%. Later measurements achieved sub-percent accuracy. The Casimir force is real. A measurable, reproducible force arising from the vacuum energy of quantum fields. The vacuum isn't empty. It fizzes with energy at every point in space. And the electron lives in that fizzing vacuum. The electron doesn't exist as a separate object floating in empty space. It's a disturbance in a field that permeates everything. Its energy can't be separated from the energy of the vacuum it lives in. They're connected, intertwined. The electron and the vacuum are not two things. They're two aspects of the same underlying quantum field structure. The electron also has a mass. Its rest mass is 9.1 times 10 to the power of negative 31 kilograms, almost incomprehensibly tiny. And because of special relativity, that mass is itself a form of energy. The most famous equation in physics says so. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is about 300 million meters per second. A squared. That's 9 times 10 to the power of 16 meters squared per second squared. Multiply that by the electron's mass and you get the electron's rest energy. About 8.2 times 10 to the power of negative 14 joules, or equivalently, 511,000 electron volts. 500,000 electron volts. This rest energy is stored in the electron just because the electron exists. Not because it's moving. Not because it's bound to a nucleus. Not because anything external supplied it. Just because mass is energy, and the electron has mass. That energy doesn't come from anywhere separate. It's inherent to the existence of the excitation of the electron field. It's the energy cost of creating an electron in the first place. If you want to create an electron, you need to supply at least this much energy. In practice, electrons are always created with positrons, because electric charge is conserved. You need at least twice the rest energy. 1,022,000 electron volts to create an electron-positron pair. Where does that energy come from? From photons. 2 photons, each carrying at least 511,000 electron volts, can collide and produce an electron-positron pair. This process is called pair production. It happens constantly in environments with very high energy photons, near the surfaces of neutron stars, in the jets of active galactic nuclei, in particle accelerators. It's observed routinely. The electron is born from light. It carries within itself an energy equivalent to its mass, an energy built into the fabric of what it means to be an electron, an energy that comes from the same place the electron itself comes from, the excitation of the quantum field. The electron also has a property called spin. Spin is a quantum mechanical property with no classical analog. The electron is not literally spinning like a top. The electron is a point particle. It has no physical size. Point particles can't rotate in the classical sense. But the electron behaves in magnetic fields as if it has an intrinsic angular momentum, as if it's spinning. The spin of the electron is always 1/2 in units of the reduced Planck constant. If you measure the spin of an electron along any axis, you always get either +1/2 or -1/2. Never anything in between. Never zero. Always one of two values. Two options. Nothing more. This is another quantization. Not just the energy, not just the orbital shape, but the spin itself is discrete. The electron can point up or it can point down. Two choices. Full stop. And here's where it gets precise in a way that is almost unsettling. The magnetic moment of the electron, which describes how strongly it interacts with a magnetic field, is directly related to its spin. In the simplest approximation, the magnetic moment should be exactly 2 times the Bohr magneton, the natural unit of magnetic moment for an electron. But the electron doesn't just sit there being a fermion. It interacts with the quantum vacuum. It emits and reabsorbs virtual photons constantly. These interactions shift the magnetic moment slightly away from the simple prediction. The corrections are called anomalous magnetic moment corrections, and they've been calculated in quantum electrodynamics to extraordinary precision by summing up contributions from Feynman diagrams of increasing complexity. The current theoretical prediction for the magnetic moment of the electron in units of the Bohr magneton is 2.00231930436. The current experimental measurement is 2.00231930436 as well. The numbers match to more than 10 decimal places. The theory and the experiment agree to better than 1 part in 1 trillion. This is the most precise agreement between theory and experiment in the history of science. Not by a little, by a lot. This is what a correct theory looks like. Not approximate, not close enough. Matched, digit by digit, to the limit of what can currently be measured. And any tiny disagreement in the final digits, once the measurements grow sharper still, might eventually point toward physics beyond the standard model. New particles, new fields, new forces. The precision of the measurement is so extraordinary that even its tiny error has meaning. The Zeeman effect is another window into the electron's energy. In a magnetic field, the energy of an electron depends on how its spin is oriented relative to the field. Spin, aligned with the field, has a slightly different energy than spin opposed to the field. This splits what would otherwise be a single spectral line into multiple lines. The Dutch physicist Peter Zeeman discovered this in 1897. He was using sodium gas and a magnetic field, and he noticed that the bright yellow spectral lines of sodium split when he turned on the field. His supervisor, Hendrik Lorentz, helped explain it using classical electromagnetic theory. Both shared the Nobel Prize in Physics in 1902. But classical theory could only partially explain what Zeeman saw. The full explanation required quantum mechanics, required the concept of spin, required the Pauli exclusion principle, required the quantization of angular momentum. The Zeeman effect is used today as a diagnostic tool across astrophysics. When astronomers observe the spectral lines from stars, they can tell from the splitting and polarization of those lines how strong the star's magnetic field is. The Sun has active regions with magnetic fields, thousands of times stronger than Earth's. Those regions show strongly split spectral lines. Sunspots are regions of suppressed convection, where the magnetic field is especially strong. The Zeeman effect reveals them. Neutron stars can have magnetic fields billions of times stronger than anything in the solar system. Those fields split X-ray spectral lines in ways that are detectable from Earth. All from the electron's energy responding to magnetic fields. All from the quantum nature of spin. Here's something else about the electron's energy that takes it somewhere genuinely strange. The electron can tunnel. Quantum tunneling is one of the strangest predictions of quantum mechanics, and it's completely real. It happens constantly. In classical physics, if a ball doesn't have enough energy to get over a hill, it stops. It rolls back down. It can never cross to the other side without enough energy. In quantum mechanics, a particle can pass through a barrier even without enough classical energy to go over it. It tunnels through. The wave function, which describes the probability of finding the electron in any location, decays exponentially inside a classically forbidden region. But it doesn't reach zero unless the barrier is infinitely thick. There's a small but non-zero amplitude on the other side. A small but non-zero probability of finding the electron there. Thin barriers transmit significant fractions of electrons. Thick barriers transmit almost none. This is the operating principle of the scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich in 1981. They shared the Nobel Prize in Physics in 1986. The device brings a metal tip very close to a surface, just a nanometer or two away. A small voltage is applied. Electrons tunnel across the tiny gap between the tip and the surface. The tunneling current is extraordinarily sensitive to the gap distance. Change the distance by a single atom's width, and the current changes by about a factor of 10. By measuring how the current changes as the tip is scanned across the surface, you can reconstruct the height of the surface at every point, with atomic resolution. The scanning, tunneling microscope can image individual atoms, can see the electron clouds surrounding them, can see how atoms are arranged on a crystal surface, can even push individual atoms around to build atomic-scale structures. Scientists at IBM used a scanning tunneling microscope to spell out the letters IBM using 35 xenon atoms on a nickel surface in 1989. All because of quantum tunneling. All because the electron's wave function doesn't stop at the edge of a barrier. It leaks through. Tunneling also makes the sun burn. The sun fuses protons in its core. But protons are positively charged. They repel each other electromagnetically. The electrostatic repulsion creates a barrier. Classically, the protons in the sun's core don't have enough thermal energy to overcome this barrier. The temperature is too low. By classical physics, the sun shouldn't burn. But protons are quantum particles. They can tunnel through the electrostatic barrier. With a tiny but non-zero probability, two protons approaching each other will tunnel through the barrier and find themselves close enough for the nuclear force to take over. The sun burns because of quantum tunneling. Stars burn because of quantum tunneling. Without quantum tunneling, there would be no stellar fusion. Without stellar fusion, there would be no heavy elements beyond hydrogen and helium. No carbon. No oxygen. No iron. No periodic table worth speaking of. The existence of everything complex in the universe depends on the electron's quantum nature and its ability to tunnel through barriers. The fine structure constant is the next piece of this. The coupling between the electron and the electromagnetic field is governed by a number, a dimensionless number, a pure ratio with no units. It's called the fine structure constant, usually written as the Greek letter alpha. Its value is approximately 1 divided by 137. More precisely, it's about 0.00729,735. This number was first identified by Arnold Sommerfeld in 1916, when he was trying to explain the fine structure of hydrogen spectral lines, the tiny splittings within what looked like single lines. The fine structure constant is the square of the electric charge divided by the speed of light times Planck's constant in appropriate units. It tells you how strongly electrons couple to photons, how strongly the electron field couples to the electromagnetic field. If the fine structure constant was 0, electrons and photons wouldn't interact at all. No light would be emitted or absorbed. No chemistry would be possible. If the fine structure constant were much larger, atoms would be much smaller, chemistry would be completely different, and life as we know it would be impossible. Its actual value, 1 divided by approximately 137, is what it has to be for the universe to look the way it does. No one knows why it has this value. There's no derivation from deeper principles. No theory that predicts it from scratch. It's measured. It's one of the fundamental constants of nature, in the same category as the speed of light and Planck's constant. The physicist, Richard Feynman, was fascinated by this number. He wrote that it's one of the greatest mysteries of physics, a magic number that comes to us with no understanding from physics of where it comes from. He said that all good theoretical physicists put this number up on their wall and worry about it. The mystery hasn't been solved. The fine structure constant is what it is. The electron couples to the electromagnetic field with exactly that strength. And that coupling is what determines the energy of every photon the electron emits and absorbs. Every spectral line, every color, every chemical bond, all of it flows from this one mysterious number. Let's bring everything together and follow an electron through its history. When the universe was very young, a tiny fraction of a second old, it was a hot, dense plasma. The temperature was so high that the average energy of a photon was far above the rest mass energy of an electron. In those conditions, electron-positron pairs were constantly being created from photons and annihilating back into photons. The equilibrium favored roughly equal numbers of electrons, positrons, and photons, all interacting constantly. There was no such thing as a stable atom. The universe was too hot. As the universe expanded and cooled, the average photon energy fell. When the temperature dropped to about 5 billion degrees, about 1 second after the Big Bang, the average photon energy fell below the pair production threshold. Creating new electrons and positrons became difficult. Existing pairs still found each other and annihilated, but new pairs were created more slowly. The annihilation rate outpaced the creation rate. Most of the positrons found electrons and annihilated into photons, but there was a slight asymmetry. For reasons we don't fully understand, there were slightly more electrons than positrons. About 1 billion and 1 electrons for every 1 billion positrons. The extra electrons had no partners. They survived. They became the electrons we have today. And they carry with them, today, the energy that corresponds to their quantum mechanical ground state in whatever atom they're eventually part of. About 380,000 years after the Big Bang, the universe had cooled to about 3,000 degrees. At that temperature, electrons could finally combine with protons and helium nuclei without being immediately knocked back off by high-energy photons. The first atoms formed. As each electron fell into its lowest energy level around its nucleus, it released a photon. Not a random photon. A photon carrying exactly the energy difference between the initial state and the ground state. Billions and billions of atoms forming across the entire universe. Each one releasing photons. The universe became transparent as electrons stopped bouncing photons around. Those photons have been traveling ever since, stretched to longer and longer wavelengths by the expansion of the universe. Today, they fill the entire sky as a faint glow of microwave radiation. The cosmic microwave background. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs. They were trying to eliminate noise from a radio antenna and couldn't figure out where this persistent signal was coming from. It was coming from everywhere, in every direction. The same intensity. It was the afterglow of the first atoms forming. The light released when electrons first settled into their energy levels. The electrons' quantum energy levels, in a very real sense, are visible across the entire sky. The most distant signal we can detect. The echo of the universe's first atoms. Written in the spectrum of microwave radiation. Written in the electron's quantized energy. The sun burns by fusing hydrogen into helium in its core. In that process, photons are produced. But the sun's core is so dense, with a density of about 150 times that of water, that a photon bouncing around in it doesn't go far. The mean free path of a photon in the solar core, the average distance it travels before being absorbed, is only about a centimeter. Every centimeter, It's absorbed by an electron and re-emitted. The sun's radius is about 700,000 kilometers. That's 70 billion centimeters. The photon has to travel that far through a medium where it can only go 1 centimeter at a time in a random direction each time. This is like trying to walk from one side of a city to the other, but after every single step you have to choose a random direction for your next step. You'd spend most of your time going in circles. The photon is doing the same thing. The result is that a photon spends somewhere between 10,000 and 100,000 years bouncing around inside the sun before it finally makes it to the surface. Every bounce is an electron absorbing a photon, jumping to a higher energy level, and dropping back down to emit a new photon. Over those tens of thousands of years, the energy that started as a nuclear reaction in the core is absorbed and re-emitted by electrons an almost incomprehensible number of times. At every step, the electron's discrete energy levels dictate exactly what energy the photon carries. By the time the photon escapes from the sun's surface, it carries the thermal energy corresponding to the sun's surface temperature of about 5,800 Kelvin. It travels through space for about 8 minutes. It arrives at Earth. It's absorbed by a leaf, where it drives a photosynthesis reaction, storing chemical energy in a sugar molecule. That sugar molecule is eaten by an animal. The energy flows into ATP, the cell's energy currency. The ATP powers muscle contractions, nerve signals, and every other energy-requiring process in the animal's body. The energy that powers life on Earth left the sun's core as a nuclear reaction over 100,000 years ago. It was relayed through tens of thousands of years of electron energy transactions. It arrived as sunlight, and it became you. The electron's energy is not abstract. It's literally the energy in your cells right now, the warmth of the sun on your face, the light that built the food you ate. All of it, the electron's energy, made physical. You might reasonably ask whether we'll ever reach the bottom of this, whether there's a final answer. A complete explanation of where the electron's energy ultimately comes from. The honest answer is that we don't know. Quantum field theory is incredibly precise. It describes electrons and photons with extraordinary accuracy. But it's not the end of the story. It doesn't include gravity in a satisfactory way. General relativity. Einstein's theory of gravity describes the structure of space and time beautifully. It predicted black holes. It predicted gravitational waves. It was confirmed by the bending of starlight around the sun during the solar eclipse of 1919, which made Einstein world-famous overnight. Every prediction of general relativity has been confirmed. GPS satellites have to correct for general relativistic time dilation, or their position calculations would drift by kilometers per day. But general relativity is a classical theory. It doesn't include quantum mechanics. And every attempt to combine quantum mechanics with general relativity runs into serious trouble. The mathematics becomes ill-defined at the Planck length, about 1.6 times 10 to the power of negative 35 meters. A scale so small that the concepts of distance and position, as we normally use them, start to lose meaning. At the Planck scale, space-time itself is believed to be subject to quantum fluctuations. The smooth fabric of space-time that general relativity describes would be replaced by something foamy, fluctuating, uncertain. We don't have a theory of what happens there. String theory is one candidate for a quantum theory of gravity. It proposes that fundamental particles are not points, but tiny, vibrating strings. Different vibrational modes of the same type of string produce what we see as different particles. Different energies, different masses, different charges. In string theory, the electron is a vibrating string in a particular mode. Its energy is the energy of that vibration. Loop quantum gravity is a different approach. It suggests that space itself is quantized, that there's a minimum length, a minimum area. That space is made of discrete building blocks rather than being infinitely smooth. Neither string theory nor loop quantum gravity has made a confirmed, distinctive, experimental prediction. We're at the edge of what physics can currently reach. And at that edge, the question of where the electron's energy comes from merges with the question of what space and time are made of what the quantum fields that the electron is an excitation of are actually running in, of what the ground state of the universe actually looks like at the deepest level. These are genuinely open questions, the most exciting questions in physics. And the electron's energy, traced far enough down, leads directly to them. Now, let's think carefully about something most explanations skip over. When we say the electron is in its ground state, what does that mean in concrete physical terms? The electron's wave function in the hydrogen ground state is a specific mathematical shape, a spherically symmetric function that peaks at the nucleus and falls off exponentially with distance. The characteristic distance, the scale over which it falls off, is the Bohr radius, about 53 picometers. The electron is most likely to be found within a few Bohr radii of the nucleus. But there's a non-zero probability of finding it anywhere, even 1 million kilometers away, even on the other side of the galaxy. The probability is absurdly small, essentially zero for any practical purpose, but mathematically, technically, non-zero. The wave function extends to infinity. This is what it means to have a delocalized quantum object. It's not that the electron is hiding somewhere and we don't know where. It's that the electron genuinely occupies a spread of space. The wave function is not a description of our ignorance. It's a description of the physical state. Now, when you make a measurement, when you ask where the electron is, the wave function collapses. The electron is found at a specific location. But here's the uncomfortable part. Before you look, the electron wasn't at that location. It wasn't anywhere specific. It was in a superposition. After you look, it's at the specific location you found it. And its energy immediately after the measurement is uncertain. Because once you've pinned down its position, the uncertainty principle says its momentum must be uncertain. Uncertain momentum means uncertain kinetic energy. The act of measuring position makes the energy uncertain. This is not a theoretical curiosity. This is the actual operational reality of the quantum world. The electron's energy and its position are linked by the uncertainty principle. You can know one with precision or the other. Never both simultaneously. The ground state of hydrogen is a state of definite energy, but it's a state of indefinite position. The electron is smeared across the orbital. That's the trade-off. Definite energy means indefinite position. Definite position means indefinite energy. The ground state chooses energy, and that choice is expressed in the spherical probability cloud, the orbital, that we calculate from the wave function. There's another way to think about the electron's energy that connects to something familiar: heat, temperature. At room temperature, everything around you is vibrating. The atoms in the air are moving. The atoms in the walls are oscillating. The electrons in those atoms are being jostled. Temperature is a measure of the average energy of random motion in a system. At room temperature, the thermal energy available to a particle is about 1/40th of an electron volt. This is the energy of atomic vibrations at about 300 Kelvin. For most electron transitions in atoms, 1/40th of an electron volt is far too small to matter. The gap from the ground state to the first excited state of hydrogen is 10.2 electron volts. Thermal energy at room temperature is about 400 times too small to bridge that gap. So at room temperature, almost every hydrogen atom in a gas is in the ground state. The electrons are not thermally excited. They sit at the floor. This is why cold gases absorb specific colors of light. The electrons are in their ground states, ready to absorb photons at specific energies corresponding to specific transitions. Heat the gas up. At 10,000 degrees, thermal energy is getting close to 1 electron volt. At 100,000 degrees, it's close to 10 electron volts. At those temperatures, thermal collisions can kick electrons to higher energy levels. At 1,000,000 degrees, electrons are being stripped from hydrogen nuclei entirely. You no longer have atoms. You have a plasma of free electrons and bare protons. The sun's core is about 15 million degrees. At those temperatures, electrons are completely stripped. The plasma at the sun's core has no atoms at all. Just free electrons and free nuclei swimming in a sea of photons and neutrinos. Temperature, then, is another source of energy for electrons. When you heat a material, you're giving the electrons more energy. Excited states become populated. Electrons jump to higher levels. When they fall back, they emit light. This is why hot objects glow. A piece of iron heated to 500 degrees Celsius glows red. Heated to 1,000 degrees, it glows orange. Heated to 1,500 degrees, it glows white hot. The color of a glowing object tells you its temperature. Because the temperature determines which energy levels are populated, which transitions are happening, which photon energies are being emitted. This is blackbody radiation. Max Planck's original problem in 1900. The problem whose solution gave us quantum mechanics. The fact that hot objects glow in a specific color-temperature relationship was known experimentally, but classical physics couldn't explain it. Classical physics predicted that objects should emit infinite energy at high frequencies. The ultraviolet catastrophe. Planck solved the problem by assuming energy was quantized, by assuming it came in packets, by writing down his equation: energy equals Planck's constant times frequency. That assumption, which Planck thought of as a mathematical trick, turned out to be a fundamental truth. Energy is quantized. The electron's energy levels are discrete. And the story of where the electron gets its energy is the same story as the origin of quantum mechanics. They're the same mystery approached from different directions. The electron's energy also plays a central role in chemistry at its most fundamental level. A chemical bond is, at its core, a shared arrangement of electron energy. When two atoms approach each other, their electron wave functions begin to overlap. The electrons no longer belong exclusively to one nucleus. they're shared between the two. In a hydrogen molecule, the two electrons from two hydrogen atoms come together. The shared arrangement has a lower total energy than the two separate atoms. The energy is lower because the electrons can access a larger region of space when shared between two nuclei. A larger, accessible region means a less confined electron. A less confined electron, by the uncertainty principle, doesn't need to have as much kinetic energy from confinement. The kinetic energy contribution decreases. The total energy falls, and the system settles into the lower energy bonded state. The chemical bond is the system choosing a lower energy configuration, choosing a larger orbital, reducing the zero-point confinement energy. That's what a covalent bond is, quantitatively, at its root. The bond energy, the energy you'd need to supply to break the bond, is the energy difference between the bonded state and the two separate atoms. For the hydrogen molecule, this bond energy is about 4.5 electron volts. That's the energy you'd need to separate those two hydrogen atoms. It's also the energy released when they came together to form the bond. Every chemical reaction is electrons rearranging their energy levels. Reactants have their electrons in certain orbital configurations. Products have electrons in different orbital configurations. If the product's configurations have lower total electron energy, the reaction is exothermic. It releases energy, the burning of hydrogen in oxygen, the oxidation of glucose in your cells, the combustion of natural gas in a stove. All of these release energy because the electrons in the products are in lower energy configurations than in the reactants. The energy released is the difference in electron energy between the starting and ending configurations. That energy shows up as heat, or light, or work, or stored chemical energy in another molecule. But it's always the same thing at the root. Electrons moving from higher energy configurations to lower ones. The electron's energy is the currency of chemistry. Every reaction is a transaction. Every bond formed releases energy. Every bond broken consumes energy. And the balance sheet of electron energies is what determines whether a chemical reaction releases heat or requires it, whether it happens spontaneously or needs to be driven, whether it's the kind of reaction you can use to do work or the kind that requires work to proceed. This is also why biology is possible. Living cells are machines that run on chemical energy. They extract energy from food by rearranging chemical bonds, by moving electrons from higher energy configurations to lower ones. The electron transport chain in your mitochondria, the chain of reactions that produces most of your cell's ATP, is literally a chain of electron energy transfers. Electrons move from NADH, where they're in a relatively high energy state, down through a series of protein complexes, each one at a slightly lower electron energy level, finally ending at oxygen, where the electrons are in their lowest energy state. The energy released at each step is used to pump hydrogen ions across a membrane. The hydrogen ions flow back through an enzyme called ATP synthase. The flow drives the synthesis of ATP. The ATP powers every energy-requiring process in the cell. You run on electron energy cascades. Every heartbeat, every thought, every movement, every moment of being alive, powered by electrons moving to lower energy configurations. The energy of life is the energy of the electron. Let's also consider what happens to the electron's energy when it interacts with magnetic fields in a material. This goes beyond the Zeeman effect we discussed earlier. In a solid material, the electrons in the outermost shells of atoms are shared across the whole material. They move through a periodic lattice of atoms. And in a magnetic field, those electrons travel in curved paths. Because moving charges in magnetic fields follow curved trajectories, the quantum mechanics of electrons moving in circular paths in a magnetic field produces a completely new set of quantized energy levels. These are called Landau levels, named after the Soviet physicist Lev Landau, who described them in 1930. The Landau levels are equally spaced in energy. The spacing between them is proportional to the strength of the magnetic field. In a strong enough magnetic field, at low enough temperatures, the electrons in a two-dimensional system, like a very thin layer of semiconductor, will fill up Landau levels one at a time. And something strange happens. The electrical conductivity of the material, how well it carries current, becomes quantized. It can only take specific, discrete values. Not just any value. Specific values. This is the quantum Hall effect, discovered by Klaus von Klitzing in 1980. He was working with a silicon transistor at very low temperatures and strong magnetic fields. He found that the Hall conductance, a measure of current flowing perpendicular to an applied field, stepped in discrete jumps as he changed the magnetic field. The values weren't just discrete, they were universal, to extraordinary precision, equal to a fundamental combination of physical constants. The square of the elementary electric charge divided by Planck's constant, times an integer. Each step was exactly 1 unit of this fundamental ratio. Von Klitzing won the Nobel Prize in Physics in 1985. The quantum Hall effect is now used as the international standard for electrical resistance. The ohm, the unit of electrical resistance, is defined in terms of this quantum Hall resistance. Because it's reproducible to extraordinary precision across different materials, different temperatures, different magnetic fields. Because it's anchored to fundamental constants of nature. The electron's quantized energy in a magnetic field is so precisely defined that it forms the basis of our measurement system. The exact same physics, taken further, gives rise to the fractional quantum Hall effect, discovered in 1982 by Daniel Tsui and Horst Sturmer. At even lower temperatures and stronger magnetic fields, the Hall conductance takes on fractional multiples of the same fundamental unit: 1/3, 1/5, 2/3, 3/7. The explanation for these fractions turned out to require one of the most remarkable ideas in modern physics. The electrons in these extreme conditions collectively form a new quantum state of matter. They behave as if new particles have formed. Particles with a fractional charge. 1/3 of an electron's charge. 1/5. 2/3. These are called anyons. They don't exist in isolation. They emerge from the collective quantum behavior of billions of electrons. The energy of the individual electron is less important than the energy of the collective state. The system forms a new kind of quantum liquid, a topological quantum fluid with properties that arise purely from the topology of the quantum state, not from the details of the individual electron energies, but from how the wave functions of all the electrons are entangled with each other. Robert Laughlin, who explained the fractional quantum Hall effect, shared the Nobel Prize in Physics in 1998 with Tsui and Sturmer. The fractional quantum Hall effect shows that the electron's energy, in the right context, is not just about individual electrons. It's about what many electrons do together. About collective quantum states that are qualitatively different from anything you'd expect from adding up individual electron behaviors. This is one of the frontiers of condensed matter physics. Topological phases of matter. states of materials with properties protected by topology rather than specific atomic arrangements. Properties that are extraordinarily robust against perturbations. Some of these topological states could form the basis of a new kind of quantum computing, storing quantum information in topological properties that are inherently protected against errors, because the information would be encoded in the topology of the quantum state, not in any single electron's energy, not in any specific physical location, but in global, topological properties of the entire system. All of this flows from the electron's energy, from the quantum nature of the electron, from the Pauli exclusion principle, from Landau levels, from the collective behavior of many fermions in extreme conditions. The electron's energy, explored far enough, leads to some of the most exotic and technologically promising physics of the 21st century. There's a story about the electron's energy that runs through the history of particle physics, and it starts with a problem. In the 1930s, physicists were studying beta decay, a neutron inside an unstable atomic nucleus converting into a proton and emitting an electron. This is radioactive decay. It happens in many unstable isotopes. The problem was energy conservation. In beta decay, the electron that comes out should carry away a specific energy. The energy difference between the initial nucleus and the final nucleus. That's fixed. That's determined by the masses of the nuclei. But when physicists measured the energies of the electrons coming out of beta decay, they found a range, not a single value. A continuous spectrum from 0 up to the maximum. Some electrons came out with almost the full energy. Most came out with much less. This was baffling and alarming. It seemed to violate energy conservation, the most fundamental law in physics. Niels Bohr, in a moment of desperation, actually suggested that maybe energy conservation wasn't exact. Maybe it was only approximately true. Wolfgang Pauli, the same man who gave us the exclusion principle, refused to accept this. He proposed instead, in a letter to colleagues in 1930, that a new particle was being produced. A particle that was invisible, that interacted so weakly with matter that it passed right through everything without being detected. This particle would carry away the missing energy, the energy that seemed to be disappearing. He called it, somewhat tongue-in-cheek, the neutron. But the word neutron was later taken by the particle James Chadwick discovered in 1932. Pauli's particle was later renamed the neutrino, the little neutral one. Enrico Fermi developed the theory of beta decay, incorporating the neutrino in 1933. The neutrino was finally detected experimentally in 1956 by Clyde Cowan and Frederick Rines using a nuclear reactor. It had taken 26 years from Pauli's proposal to the experimental confirmation. The story of the neutrino is directly connected to the electron's energy, because the neutrino was proposed specifically to save energy conservation in a reaction involving electrons. And the neutrino turned out to be real and extremely strange. The neutrino is nearly massless. The current upper limit on the electron-neutrino mass from experiment is about 0.45 electron volts. For comparison, the electron's mass is about 511,000 electron volts. The neutrino weighs less than 1 part in a million of what the electron weighs. Maybe less. We don't know the exact mass, only that it's incredibly small, but not zero. The neutrino interacts only through the weak nuclear force and gravity. Not through the electromagnetic force. Not through the strong force. This makes it extraordinarily difficult to detect. A neutrino can pass through a light year of lead with only about a 50% chance of interacting. 1 light year through solid lead, and 50-50 odds of not leaving a trace. Right now, about 65 billion solar neutrinos pass through every square centimeter of your body every second, arriving from the nuclear reactions in the sun's core, passing straight through Earth, through you, through everything, as if it weren't there. You don't feel it. You can't feel it. They're too weakly interacting. The existence of the neutrino, this ghost particle that passes through everything, was deduced by following the electron's energy, by noticing that some energy seemed to be missing, by refusing to abandon energy conservation, by proposing the unseen, and by eventually finding it. The electron's energy conservation led us to the neutrino. The neutrino changed our picture of the particle world. It turned out there are 3 types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, corresponding to the 3 generations of matter. The electron belongs to the first generation. The muon, a heavier cousin of the electron, belongs to the second. The tau particle, heavier still, belongs to the third. Each has its own neutrino. The standard model of particle physics, the theory that describes all known fundamental particles and forces, except gravity, is built around this structure. 3 generations, 6 quarks, 6 leptons, including the 3 charged ones and 3 neutrinos, 4 fundamental forces, 12 force-carrying bosons, and the Higgs field, which gives mass to particles through their interactions with it. The electron sits near the bottom of this structure, the lightest charged particle, the most stable, the one most easily accessible, the one whose energy we can measure most precisely. The electron is the hydrogen atom of particle physics, the simplest, most accessible, most thoroughly understood example of the underlying structure, and its energy, followed carefully, leads into the full architecture of the standard model. The Higgs field deserves its own mention here, because it connects directly to where the electron gets one component of its energy: its mass. In the standard model, particles acquire mass through their interaction with the Higgs field. The Higgs field fills all of space, similar to the other quantum fields we've discussed. But the Higgs field has a special property. Unlike the electromagnetic field, which has a ground state energy of 0 for its field value, the Higgs field has a non-zero ground state. The vacuum value of the Higgs field is not 0. It's about 246 billion electron volts in natural units. This non-zero vacuum value is the key. Particles that interact with the Higgs field are constantly being jostled by it. They interact with the field, and that interaction slows them down. It resists their motion. It gives them inertia. Inertia is mass. The stronger a particle's interaction with the Higgs field, the more mass it has. The electron's coupling to the Higgs field is described by a number called the Yukawa coupling. For the electron, this coupling is about 2.9 times 10 to the power of -6, a very small number, which is why the electron is so light, compared to, say, the top quark, whose Yukawa coupling is close to 1. The top quark is about 340,000 times heavier than the electron, because it couples much more strongly to the Higgs field. The electron's mass comes from its interaction with the Higgs field. The Higgs field's non-zero vacuum value was established in a phase transition in the very early universe, a fraction of a second after the Big Bang. Before that transition, the Higgs field was zero. All particles were massless. They traveled at the speed of light. After the transition, the Higgs field settled into its non-zero ground state. Particles that couple to the Higgs acquired mass. They slowed down. The electromagnetic and weak forces, which were unified before the transition, became distinct. The universe changed character in that moment, and the electron, which before that moment was massless and flying at the speed of light, suddenly had mass. Suddenly had rest energy. Suddenly could be bound to nuclei to form atoms. The mass of the electron, the 500,000 electron volts encoded in E equals mc squared, came from the Higgs mechanism, from a phase transition in the early universe, from the Higgs field settling into its ground state. The electron's energy includes the energy of its rest mass, and that rest mass came from the Higgs field. The Higgs boson was discovered at CERN in 2012. This confirmed the mechanism experimentally after decades of theoretical work. Peter Higgs, who proposed the mechanism in 1964, shared the Nobel Prize in Physics in 2013 with François Englert, who independently proposed the same idea at the same time. The electron's mass, one component of its energy, came from the Big Bang, from a phase transition a tiny fraction of a second after the universe began, from the Higgs field choosing its ground state. Now consider what it means that the electron's energy is stable. Not just stable for a while. Stable, as far as we can tell. The electron appears to be completely stable. It doesn't decay. It doesn't fall apart. You can't do anything to make an electron spontaneously turn into something lighter, because there's nothing lighter with the same charge. The positron has the same mass but opposite charge. It's not lighter. There's no lighter charged particle, so the electron has nowhere to go. It can't decay while conserving both charge and energy. By the Noether theorem, named after the brilliant mathematician Emmy Noether, who published it in 1918, conservation of charge is linked to a fundamental symmetry of the laws of physics. The laws are symmetric under a certain type of transformation called gauge transformation. That symmetry leads directly to charge conservation. Charge conservation means the electron cannot simply vanish. It can be annihilated with a positron. But both the electron and the positron have to be present, and the net charge has to be conserved. So, the electron carries its charge, and its charge carries it. The electron's stability is guaranteed by the conservation of charge, by the symmetry of the laws of physics under gauge transformation, by Noether's theorem, by the deep mathematical structure of reality. The electron you breathe in today will still be an electron in a trillion years, assuming nothing extraordinary happens to it. No decay, no change. An electron is an electron is an electron, forever. The most recent experimental lower bound on the electron lifetime is enormously long. Current experiments have set a lower limit of more than 10 to the 28th years on the electron's lifetime. The current age of the universe is about 13.8 billion years. 10 to the 28th is about 1 trillion billion times that. The electron has outlasted the universe by an unimaginable margin already, and there's no indication it will ever stop. Its stability is one of the most remarkable things about it. And that stability, tied to the conservation of charge, tied to gauge symmetry, is part of why the electron's energy is so stable. The ground state energy doesn't decay. The electron doesn't lose its mass energy. It doesn't radiate away its rest energy. The laws of physics forbid it. Symmetry forbids it. Conservation laws forbid it. And so the electron carries its energy indefinitely. One more thing before we look at the full picture. The electron experiences something in modern quantum field theory that's called the electron self-energy. This is the effect of the electron interacting with its own electromagnetic field. An electron moving through space creates an electromagnetic field around itself. That field has energy, and that energy is associated with the electron. It's part of what the electron is. In classical electromagnetism, the self-energy of an electron calculated by assuming it's a point particle is infinite. The energy density of the electric field near a point charge diverges. The total energy is infinite. This was a problem that classical physics never resolved. Quantum electrodynamics faces a similar issue. The naive calculation of the electron's self-energy in QED also gives an infinite result. But the infinities are different in character than in the classical case. And in QED, they can be handled through renormalization. The idea of renormalization is that you split the electron's properties into a bare part and a correction part. The bare electron has some bare mass and bare charge. The corrections from the self-energy interactions add to these. The sum of the bare properties plus the corrections equals the physical, measurable properties. The bare mass is infinite. The correction is also infinite. But they're infinite in just the right way that their sum is finite and equals the measured electron mass. This cancellation of infinities is the mathematical machinery of renormalization. Feynman, Schwinger, and Tominaga showed how to do this systematically, how to organize the infinities, how to ensure they cancel properly, how to extract finite, meaningful predictions from a theory that produces infinities in naive calculations. The resulting finite predictions are extraordinarily accurate. But the procedure is strange. You're subtracting infinity from infinity and getting a finite answer. Mathematically, infinity minus infinity can be anything. It depends on how you approach it. The procedure for renormalization specifies exactly how to approach it. Which infinities cancel which others. The result is well-defined and precise. But it has troubled physicists since it was developed. Dirac, who was one of the founders of quantum field theory, never accepted renormalization. He spent decades trying to develop a self-consistent theory of the electron that didn't require it. He never succeeded. Feynman described his own procedure as a dippy trick. He knew something was being swept under the rug. He just didn't know what. We still don't know exactly what. The fact that renormalization works so well is both a triumph and an indication that something deeper is waiting to be understood. That, at some scale, perhaps the Planck scale, a more complete theory takes over that resolves the infinities properly, without the mathematical trick, without the cancellation. Just finite results from the start. Nobody has found that theory yet. What we have is QED, with its renormalized predictions that agree with experiment to 11 decimal places. It works, and we don't fully understand why. All of this, the electromagnetic interaction, the uncertainty principle, the Pauli exclusion principle, the quantum field theory, the Higgs mechanism, the gauge symmetry. The renormalization comes together to describe one thing: the energy of the electron. An energy that traces back through every layer of physics we know, through atomic physics, through solid-state physics, through particle physics, through cosmology, through the early universe, through the phase transition that gave particles their mass, through the Big Bang itself, and then into the realm of open questions, of Planck-scale physics, of quantum gravity, of whatever it is that determines the values of the fundamental constants. The electron's energy is not a simple thing with a simple origin. It's a thread that, pulled on, unravels the entire fabric of modern physics. What we know is impressive. What we don't know is vast. And the boundary between the two is exactly where the most interesting work is happening. The next time you turn on a light, you're watching electrons fall. From higher energy levels to lower ones, releasing photons as they go. Each photon carrying the exact energy difference between the levels. Each color a specific number of electron volts encoded in the frequency of the light. The next time you feel warmth from the sun, you're absorbing the final step in a chain of electron transactions that started in the sun's core over 100,000 years ago. Energy that has been absorbed and re-emitted by electrons more times than words can easily capture. The next time you hold something solid in your hand, that solidity is the Pauli exclusion principle. Electrons refusing to share a quantum state. The electron C in the atoms of your hand pushing back against the electron C in the atoms of the object. Not because of any mysterious force reaching between them. Because fermions cannot overlap. Because the mathematics of quantum fields does not allow it. Every sensation of solidity you've ever had. Every surface you've ever touched. Every object that has held its shape instead of passing through another. All of it is the Pauli exclusion principle. The electron's quantum nature, invisible and strange, is the foundation of everything tangible. And that's the deepest answer we have. An electron gets its energy from the same place everything gets its energy from the structure of the universe, from the laws that govern it, from the quantum fields that fill it, from the constants of nature that no one has explained. The electron doesn't have energy because something gave it energy. The electron is energy, frozen into a specific form, quantized, bound, governed, and running on rules that have never changed. Not in 13.8 billion years. Not across the full span of the observable universe. Not even a little. Good night.